Hi everybody and welcome to a new video in the Solid Principles for Machine Learning Engineers series. Last time we checked the single responsibility principle. Today we move on to the all letter in the SOLID acronym. The all letter stands for open closed principle. Let's check out its definition. The open solid principle says that software entities, for example, classes, modules, methods, or functions, should be open for extension but closed for modification. This means that if you have code with a bunch of software entities that have certain functionalities and you want to add a new functionality, what you shouldn't do is modify a current entity that you have. For example, adding functionality to a class that you already wrote, but rather have the code that's modular enough so that you can add the new functionality as a new software entity, for example, as a new class. It could be that you feel that this definition is a little bit mysterious still, and that's totally fine, but don't worry because we're going to have a practical example where we'll just clear out all the doubts you may have. Before getting to the Python example, let's check out the problems you may face if you violate the open-closed principle in your machine learning code. Here you have two main problems. First, your classes are going to be tightly coupled. This means that if you want to change one bit of code, you have to change it in a bunch of different classes. And of course, this is a hassle because the code is not maintainable. At the same time, testing this type of tightly coupled code is very difficult because it's difficult to separate out all the different parts of it and testing them in isolation. How can you spot if you're violating OCP? Well, you can ask a simple question. Does a class know too much about its dependencies? Say you have a class with an attribute, and this attribute is an external object. Now, if your class looks too much into that object, for example, it knows about the strategy that that object utilizes to carry out a certain job, well, then you're violating the open-closed principle. Again, this may feel a little bit abstract, so let's move on to a Python example. In this Python example, we have a minimalistic deep learning pipeline where we'll deal only with feature extraction. So we want to keep things extra simple. And we assume that we'll be dealing also with audio data. Okay, let's start from the extractor class. So here we have a couple of methods. So one extracts spectrograms, which is an audio feature from audio data, and the other one is extract MFCC. MFCCs being another type of audio feature you can extract from an audio time series. Okay, so how do we use this extractor object in DL pipeline? Well, we pass it in the constructor and then we register it in the self.extractor attribute. In the constructor, we also pass feature type, and this is a string that could take a couple of values, either spectrogram or MFCC, depending on the type of feature that we want to extract. Then we have a public method. This is the main method, run, where we pass some data and then we run through all the DL steps. For the time being, as I mentioned, we'll be only extracting features, and for that we'll be using this underscore extract private method. Now let's take a look at this private method here. Well, here we have a conditional statement. So if the feature type is spectrogram, then we'll offload the extraction of spectrogram to the extract spectrogram method of the extractor object. If it's MFCC, then we'll use extract MFCC method. Now, of course, just like a quick note, so here, of course, we're not really extracting any type of data. These extraction methods are simply stops, but this is like totally fine for the example at hand. Okay, so now let's run this. I have like some super dummy data. I instantiate an extractor, I pass it in here in the DL pipeline along with a feature type, the spectrogram, and then I do a DL pipeline.run. So let's run this and see the results. Yeah, and this works. So we are running the DL pipeline and we extracted the spectrogram. Great. Now, there is a problem with this design that violates the open-closed principle. And now we'll see why this is the case by switching to the design of this example. So here we have the design. So we have the DL pipeline class that owns an extractor instance. The owning relationship is indicated through this arrow. So DL pipeline owns an extractor. Now, extractor has a couple of methods. So one is, of course, extract MFCC. The other one is extract spectrogram. So what's the problem here? Well, what if we want to add a new type of audio feature extraction? So for example, what if we want to add MEL spectrogram extraction? Well, in this case, what we have to do is change the code to modify two entities rather than adding this new functionality to a new entity. So what are the entities that we should modify? Well, first of all, we should modify extractor by adding a new method, which I can call extract MEL spectrogram. And I'll pass the data here and I'll do a print extracted MEL specs. And then I'll also have to change or modify DL pipeline. And specifically, I have to go in this underscore extract private method and add another elif statement here that says that if self.featureType this time is equal to MEL spectrogram, then there's a syntax error here. I want to do a self.extractor.extract MEL spectrogram, and I'll pass the data in. So you see the problem, right? So we are violating the open-closed principle here because in order to add a new functionality, we had to change the code in two places. First, the extractor, then DL pipeline. Let's ask the question to check whether a class violates the open-closed principle. In this case, we should ask, does DL pipeline know too much about extractor? And the answer, of course, is yes. And it's yes because here in the extract private method, DL pipeline knows about the different methods for extracting different audio features, and it offloads the audio feature extraction to the right type of method depending on the feature type. And of course, this is knowing too much about what extractor does, which makes the class violate the open-closed principle. How can we solve this issue? The answer is polymorphism. Let's take a look at the design as is right now. Now, what we want to do is to create an interface at the level of the extractor. So the extractor is going to become an interface or an abstract class that's going to have a single method, public method, that's called extract, and the only argument will be data. Now, the next step will be that of using extractor as an abstract class and then having a series of concrete classes which inherit from extractor and actually implement the abstract class. So, in order to do that, what we'll do in this design is inverting the direction of these arrows here, like that. Now, this empty arrow now means that this guy here, spectrogram extraction, is now a class that implements this interface. So MFCC extraction, spectrogram extraction, and MELSpec extraction are subclasses of extractor, or we should say concrete extractors, and they will implement the extract interface here, but using different strategies. Hence the polymorphism that we mentioned earlier. Let's implement the extractor interface first. For that, I want to import from ABC abstract method as well as ABC. These are functionalities that Python provides us with in order to create abstract classes. So the extractor class is going to inherit from abstract class, and it will become, because of that, an abstract class. And then here we'll have our main interface method called extract, and here this is an abstract method, and of course here, given this is an abstract class, will just pass. Okay, so what next? Well, we have to implement one concrete extractor for each of these functionalities that we had here. So we'll start with the spectrogram extractor that inherits from extractor, and here we implement, this time around we actually do the implementation of this abstract method, and for that we'll just take this. Okay, so now I can drop this method. Okay, so this is the first step. So spectrogram extractor is ready. Now the second, as a second, I want to create a mel spectrogram extractor. So this is another concrete extractor class. So let me just get rid of this because I'm getting confused. Okay, so here, same thing, only difference is the implementation, and here we should say extracted mel spectrogram. Okay, and finally, we'll implement the concrete MFCC extractor. And here we'll say extracted MFCCs. Great. Okay, so now we have this extractor framework basically, so where we have the interface on top, and then each concrete class is going to extract one specific type of audio feature. Great. So how do we change DL pipeline? Okay, first step. So we no longer need feature type because the information about feature type is embedded in the extractor, because one concrete extractor only extracts one type of feature. So we can drop this. Then the bigger change will happen here in underscore extract, where we'll get rid of this horrendous conditional statement, which was the cause of our open-closed violation. And here we'll just do a self.extractor.extract, and we'll pass the data. Great. So now, why is this a good design? Well, this has solved the open-closed violation because in this case, as you can see here, DL pipeline doesn't know anything about the strategies used by the extractor in order to extract different features. All it knows is the interface, the extract interface. And so whenever we want to add a new piece of functionality, we can easily do it by adding a new concrete extractor that inherits from the extractor interface or extractor abstract class. So DL pipeline is now, as well as extractor, are now close to modification, but they are open to addition of new functionalities. Okay, so the last thing that remains to do is to change this script. Let's modify it. So instead of extractor here, a generic extractor will say spectrogram extractor. So we'll instantiate this, then we'll pass it in here. Then we should get rid of this feature type argument because we no longer have it. And then we run this. And here we go. It works. So running DL pipeline and extracted spectrogram. So now this design is a clean design that respects the open-closed principle. That's it for the open-closed principle. I hope you found this video useful. If that's the case, please remember to leave a like. And if you're not subscribed to the Sound of AI channel, please do subscribe and hit the notification bell. I'll see you in the next video. Take care.